Yeah, see, this is visually disturbing.
Yeah. Well, and part of the thing you probably don't like about it is I've got multiple logarithms in there, right?
Mm-hmm.
If
Well, the x
only
minus 2 is terrifying.
it is. But do we have a tool that says what we can do if we have one logarithm plus another logarithm? If only we had some tool that would tell us what to do with that.
Well, if we can break them apart, can we put them together?
Absolutely. That's the same as log base 2 of x times x minus 2 equals 3. Okay. Well, if only we had
question.
What's that?
I have a quick question.
Shoot.
So in my brain, I would add the x to the other x and be like 2x minus 2, obviously.
So how about x squared minus 2x?
Yeah. I guess I just don't 100% understand them multiplying it, like where that comes from.
Well, that comes the fact that these are two exponents, right?
Right.
Oh, when do we add exponents? Well, we add exponents when we multiply things together, right?
Mm-hmm.
So we add exponents when things are multiplied together.
Okay. Thank you.
And believe me, it is a weird thing to do.
It just feels really foreign.
And that's one of the, I talked a little bit about the transcendental functions. These logarithms and exponents are some of our first transcendentals. And what that means is that they transcend the rules of algebra. So they give us manipulation power that algebra doesn't have on its own. Yeah. So in some ways, they should be things that feel like they break the rules.
They do feel they feel outlawish.
And they're not. They're based on something we're extremely familiar with.
Right.
I mean, you do this just almost without thinking nowadays.
Yeah.
But thinking of it in this logarithmic way, that just seems like a completely foreign animal.
Yeah. Okay.
And it should for a while. That's okay.
I'm glad I'm on the right track then.
And I think most of what makes logarithms difficult, the mechanics for logarithms are not that tough, but the visuals of what it looks like, what I'm supposed to do with it, and the lack of building up visual cues for it makes it difficult. You know, if I give you something that looks like, say, 3x minus 5 equals 2x plus 7.
Right.
It's almost hard to look at that without seeing the 5 move over and the 2 move over. Your brain just visually wants stuff to happen there, right?
Right. That comes very naturally compared to this.
But if you see, say, log base 3 of w is equal to, I don't know, 5.
So would that be 3 to the power of 5 is equal to w?
Yeah. And after a while, you start getting real confident with it.
Better about that.
And you start to see that movement occur.
Right.
Fair? So back that up over here. What could we do with log base 2 of this stuff equals 3?
We could do that. Okay. All right. So 2 to the power of 3. And then it just becomes an algebra.
Right. Now it's just x squared minus 2x equals 8. And you can solve that.
Yeah.
Got to be a little careful with your domain restrictions, but other than that.
My brain always jumps to factoring. Oh, good. That's correct then.
Very reasonable to do so. Should always be trying to factor first. If it doesn't work, you have other tools. But now, as I said, you got to be careful with our domain restrictions. Remember, our logarithms can't act on negative values.
Okay.
So we got to throw out that -2, because that -2 would make both of those statements negative.
Okay.
So our only answer would be that x equals 4. Yeah, mechanically, that's not too tough, but kind of visually and being used to and seeing what the path is through it,
Right.
that takes time.
Well, I'm glad that at least it sounds like I'm in a spot that is reasonable.
Oh, absolutely.
I'm not doing horrible.
And all of these have logarithmic equivalence. Like this one says, okay, when we multiply, we add exponents. This says when we divide, we subtract exponents, right?
Right.
So again, logarithms ask what happens to the exponent on a common base when we have things that are divided. Well, what happens to the exponents on a common base when we have things divided?
Subtracted.
And specifically, you take the exponent of that common base of the top one, right? And you subtract the exponent on that common base of the bottom one.
Okay. I feel like I'm on the verge of it clicking. So, like, I get it, but I got to train my brain.
Oh, yeah. And, and that's one of the reasons I say I want to focus on what are these logarithms saying to us? What are they talking about? Because if you just try to memorize these as, as rules without any context, then they're really hard to keep straight because they're weird.
They are weird.
But if you can think, well, what happens to exponents when we divide? You know what happens to exponents when you divide. You subtract the exponents.
Okay.
It just takes a while to keep it straight. This is the fun one, actually, the power rule here. Again, what happens to the exponents on some base, and here that base is x. Here those bases are just b, just notationally, right? What happens to exponents when we have something raised to a power?
Multiply it.
Multiply. So you take the power and multiply it by the exponent on the other thing, right? So we take that new power and multiply it by the exponent on the original thing.
Oh, see, that one's always the weirdest to me.
It is, but it's the really powerful one.
Yeah.
It is the one that feels like we're cheating so much.
Yeah, no, it just feels wrong.
But let's look at an example here. What if we had, say, log base, I'm going to use base 2 because base 2 is nice, of 8 to the 5th. Do you know what 8 to the 5th is?
No.
Me either. I have no idea. That fair? No idea what 8 to the 5th is. But according to this power rule, we should be able to take that 5 and pull it out as a multiple, right?
Yeah.
So 5 times log base 2 of 8. Well, what's log base 2 of 8?
That's, oh, am I supposed to use my calculator or am I supposed to translate it?
Supposed to translate. Well, not even translate, read it. Log says what's the power, right? So what power of 2 makes 8?
Oh, 3. Wait, can you repeat what you just said? Logs means
what power of?
Log. Okay.
The base makes the argument. So for example, if we said, something like log base 3 of 81, 3 to what power makes 81? This essentially translates to, if you want,
Of the base.
81 equals 3 to what power?
I'm sorry, I was writing stuff down. What did you say?
So the statement of log base 3 of 81, if log base 3 of 81 equals something, then 3 to that power should equal 81.
Oh my gosh, that makes so much more sense. 81.
And again, it's the same logic of if we write, say, 6 divided by 2 is equal to what? Well, we don't do division. You ask yourself 2 times what equals 6, right?
Right.
That's how you do a division problem. You ask what the multiplication would have to be. Logarithms are the same way. We don't do the logarithm problem. We ask, what would the exponent have to be? Because logarithms are the inverse of exponents.
Okay. That was just like an aha moment right there.
Now, we'd have to know that 3 to the 4th is 81 to be able to say that that's 4.
Mm-hmm. Okay.
So back over here, that 5 times log base 2 of 8, log base 2 of 8 is 3. So this is equal to 15, right?
Yeah.
However, what is 8? 8 is 2 to the 3rd, right?
Mm-hmm.
So this is, 2 to the 3rd to the 5th, right? What's 2 to the 3rd to the 5th?
2 to the 3rd to the 5th is...
Well, what's the 5 times 3?
Oh, it's the 15?
15. Well, why'd you multiply those?
Because that's the exponent law.
Why did we multiply these?
It's the same law.
Because of the same law. It's the same multiplication.
Yeah.
And then this down here, this might look really weird, but this asks, literally, log again says, what's the power? So 2 to what power is 2 to the 15th?
2 to the power of 15.
Yeah, 2 to what power is 2 to the 15th? Well, 2 to the 15th is 2 to the 15th.
Right.
It's almost a dumb question, right?
Almost.
Because log base 2 and exponent base 2 are inverses.
Okay.
It's like asking one of my favorite questions. Yeah. Well, they technically cancel is a bad word. They undo each other.
Yeah, no.
But if I ask something like, what is half of the double of 7?
Oh. It's just 7.
It sounds like a dumb question though, right?
Yeah.
This is, log base 2 of 2 to the 15th. It doesn't sound as dumb.
Right.
But it's really asking. Yeah. 2 to what power is 2 to the 15th? Well, 15, duh.
Yeah, okay.
Do you ever do this, by the way? Take half of the double of stuff?
No.
You do it all the time.
Half of the double?
Solve that.
2x minus 5 equals 7?
Yeah.
Okay.
What do you do first?
I add the 5 to both sides.
Okay. So you take 5 more than 5 less than a thing.
Okay, fair.
What do you do next?
You divide it by 2.
You take half of the double of x.
Okay. So it's not dumb. It's just used to undo.
Yeah. It just sounds really weird.
Yeah, it does.
But that's what we do whenever we're undoing anything.
Okay.
So for example, if we have, say, log base 5 of 5 to the x, what are we going to end up with?
Is it just 1?
Well,
or no. Wait. So it's x? Yeah.
Yeah.
Yeah. Okay.
because again, those are inverses. That's their job.
Right.
Is to undo each other. Now, it doesn't look quite as compelling as, say, the cube root of x to the 3rd.
Right.
But that's because you're used to that notation.
Yeah, that just
those
clicks.
look like they're supposed to undo each other. But why? Because this is a weird shaped line.
Yes.
And why? Because that 2 is underneath that 2. Yeah, because they're visually used to it.
It's more familiar, yeah.
Yeah. Are you visually familiar with the log base 5 notation yet?
Nah, but I might be someday.
But the first time somebody wrote that, everybody
Right.
is like, what are you talking about?
Yeah.
You know?
No, I remember, I think I probably saw stuff like that beginning in Math 95, and I was like, what is this crap?
Mhm.
So I guess my brain's just trying to go through that process again.
And it takes a while to get used to them. But the nice thing is, again, once you're used to them, they not only are actually a fairly simple mechanic to do. Nothing mechanically that we're doing is terribly difficult.
Right.
And they give us a lot of manipulation power that we didn't have before. We can manipulate things with logarithms in them in ways that we can't manipulate anything else. And that gives us tools, and that gives us power.
I feel like I shouldn't have this much power over math.
Oh, and that is actually one of the risks when you start doing a lot of logarithmic manipulation, is it feels like you can do like anything with it. So you start making up your own rules. Like, one of the biggest ones is, like you were saying with that x minus 2, you start suddenly seeing, log base 2 of x plus 3, and people start going, oh, I can do log base 2 of x plus log base 2 of 3. And you can't.
Right.
And none of those rules said we could.
Right.
Some of them kind of look similar to that. But this, of course, would be the log base 2 of 3x, right?
Yeah, because, well, I guess I want to say like the inverse of a log where we're adding something is multiplying. Is that
Yes.
language correct? Okay. I don't know if it would be appropriate to call it an inverse, but.
Yes, because it is an inverse of an exponential. So you're referencing the exponential rule.
Right.
And that this is the reverse of that. So, yeah.
Okay. But yeah, that makes sense. Sweet.
Now, have you played with your common logs?
Is that just the log base 10?
Yeah.
Not a ton. I did a little last night, and I was kind of getting it, but kind of confusing myself.
You're comfortable with the idea that if we don't write a base down there,
yeah, if it's just 10,
then it's implied that there's a 10.
Right. That's cozy enough for me.
Yeah. So what would the common log of 1,000 be?
So we're just asking 10 to what power equals 1,000?
Yeah.
Right. That is, I want to say 10, but I'm not certain. No, that's way too big. 10. What is it, like 4? 3? Oh, 3.
Yep.
Yeah, so this is stuff I was playing with last night, and it's kind of, we're getting there.
But you can see, hopefully, how much more you have to grab it with when you're thinking of the exponents as well.
Oh, 100%. Yeah.
If you try to just get it based on, following the rules and not having anything to anchor it to, it's tough. Oh,
no, it makes 1,000 times more sense now that you drew the correlation of the exponents being the inverse. I don't know, the sister function stuff of logarithms. Yeah. Okay. So now that I'm looking at my problems that I was unable to even think about last night, it looks so much simpler. Do you mind if I try one out and see?
No, not at all.
Okay. I'm just going to try out the first one on there and see if I'm the queen of logs now. Okay, I think I've already confused myself.
Would
I
you?
guess huh?
What'd you do?
So my first thought is to compile them. So I want to like multiply. I don't know what it's called, but the 4x to the power of 9 and the 2x to the power of 5. I don't know.
The arguments of the function.
The arguments?
Yeah.
Okay.
If you have, say, f of x, that x is the argument of the function.
How aggressive.
Sorry. So that's your function name, and that's the function's argument.
Okay. Yeah.
Right?
So
So when we have log base 3, that log base 3 is essentially just the name of our function, and x is the argument.
okay. I don't know why math is arguing with itself, but yeah. So my instinct is to try it, right? Who knows? To try to multiply the arguments.
Okay. What do you get when you multiply the arguments?
I get, let's see, 8x to the power of 14.
Okay. And what's happening to that 8x to the 14th?
What do you mean?
Well, what happens to that log base 7?
Oh. Just vanishes. No, we're taking the log base 7 of it.
Right. Of that product.
Of, yeah. Of our new argument. And so would we then multiply all of it by 14?
No, you're done. Because you were asked specifically to what we asked to do. As a single logarithm with a coefficient of 1.
Oh my goodness.
So you're supposed to have a 1 up there. So
okay.
Yeah, that's it.
Do we need to put the 1 up there?
No.
Or just it's implied? Okay. Wow.
And just to be clear, you couldn't bring this 14 down anyway.
Okay.
Because that 14 isn't a power of the entire argument.
Would it have to be outside of the parentheses?
Right.
Okay.
If you really wanted to, and don't do this, but you could say the 14th root of 8 to the x to the 14th, and you could bring it down. But I'm guessing you don't want to do that.
I'm not a mental masochist. I think I'm good.
Fair enough. But if you really needed to, like I need that 14,
right.
Okay, pull it out. You can grab
absolutely have to have it. Yeah. Okay.
But yeah, that's that entire problem.
Wow. That's so much easier than I was trying to make it. I guess I should probably read instructions a little better. It helps.
I encourage it.
Blindly going into math problems is not a grand idea.
It has disadvantages. What about that next one?
8. Let's see. 7x. Okay. I took a picture of the little comparison thing you did. I'm gonna pull that up really quick. So what do we do? Division of the arguments? Okay. Log base 8. And that's okay. Okay. Sorry, I had to walk through the steps of like subtracting from the top and then moving the negative down. I don't know why my brain had to
have that step like that. And then, ooh, yeah, you could even do that over, 7x to the 9 minus 1 if you wanted to. You can have all kinds of fun with that.
Yay.
Yep.
And then we arrive at the same thing.
Yep.
Cool. Okay. That makes a billion times more sense. Exponentially more sense. Okay. So the next one is visually disturbing. My new favorite term for math.
What is log base 4 of 256?
It is a number I should know off the top of my
Not necessarily,
head.
but if it's going to be some nice number, then it should be some power of 4, right?
Right.
So
So for the fourth.
4 to the 4th? Okay, you try 4 to the 4th. You go, oh yeah, 4 to the 4th is 256. Nice.
Okay, so then
Four plus
4, so it's 6. It ends up being 6 plus, or 6 minus. Yeah.
4 to what power is 2?
Huh?
What about that
Oh,
log
2.
base 4 of 2?
4 to the power of, I'm sorry. What?
4 to what power is equal to 2?
Is it?
Is it
just, oh, it's half.
It's half because it's a square root.
Right.
Exactly.
Yeah. I'm bringing in the root functions now.
Mm-hmm.
It's funny now that you mention it, I have to think of everything like with its other thing. I don't know. That didn't make sense. But to think of exponents like that, I have to think of the root. Okay. Wow. So it just simplified down to that much? Wow. Okay. All right.
Now, arguably, you could have gone, well, that's 256 times 16
Oh, no.
divided by 2 to the 6th. Fair?
Yes, but
Yeah,
that's
that 6 comes up. Well, unless you know that, 16 is 2 to the 4th, right?
Right.
And 256 is a power of 2.
Right.
What power of 2 is it? It's 2 to the 8th.
8, yeah.
So that's 2 to the 12th over 2 to the 6th. Right?
Right.
Which is 2 to the 6th. Right?
Right.
Now, that's kind of, it would certainly be nice if those matched, right?
Mm-hmm.
Okay, so how about log base 4 of 2 squared to the 3rd?
Oh, I'm getting fancy now.
Yeah, so that's log base 4 of 4 to the 3rd, which is?
Well, that's just 3, yeah. I like the other way of going about it, but
Oh, absolutely. But that's because those numbers were fairly cherry picked, right?
yeah.
The less cherry picked they are, the less nice path you get. But
Okay.
But it's nice to see that however you manipulate it, you end up in the same spot.
Right. It boggles my brain though, because it looks so complex and then it ends up being such a simple number.
Right.
Okay.
But yeah, and that's only because each of those numbers are a clean power of the base.
Mm-hmm. Yeah, they picked lovely numbers for that one.
But even if they weren't lovely numbers, that would just mean this would turn into some ugly number, right? And we'd
Right.
have log base 4 of that ugly number. Okay.
Okay. Yeah.
would be
I
done.
mean, sweet. This is making a lot more sense. I really appreciate it.
Oh, sure.
And so on the next one, just so I know, it's the argument is dividing itself. So we would just do subtraction on that, right?
To start.
Yeah. And then
So you'd have
proceed.
common log of x to the 17th y squared minus the common log of z to the 11th, right?
Uh-huh.
But then what would you do?
What would I do? That's a good question. I want to put exponents in the front, but I don't know if that's right.
Well, wanting is never wrong, right? But is this whole thing raised to a particular power?
No, it is not.
What's in the way of that happening?
Parentheses.
Well, the fact that those two things are multiplied, right?
Oh yeah.
If only we had a way to break up multiplication.
Gee, if only. So do we then divide this?
Well, how do we break up multiplication in
Or
logarithms?
do we just put them in their own little bubbles? So would we take the common log of x to the 17th and common log of x or y to the 2nd?
What operation connects those?
Addition.
Addition, because you're breaking up multiplication in a logarithm. So yeah,
Right.
it becomes an addition. Now each of your arguments are to a single power.
Right. And so now would we move the exponent to the front?
We certainly could.
I just really want to do that, I guess. I don't know.
Oh, it's nice to do.
I just want to feel powerful. Manipulate math aggressively.
It is called the power rule for a reason.
Right?
It's actually called the power rule because it's on the powers, but
no, it's just because it bestows a lot of power on you.
It really does, and I have often made that joke. It is the powerhouse rule.
It's the mitochondria of math.
Exactly. Anything that allows you to take, say, we'll use natural logs because we haven't yet. Say the natural log of the square root of 5. Like, oh, square root. Oh, I hate square roots.
Right.
Okay. Go 5 to the 1/2.
And
that's 1/2 natural log of 5. Anything that's going to take a square root and go, I don't want a square root. I'd rather multiply by a half. Like it.
Yeah.
And that's why when you learn some more sophisticated techniques, you'll have problems where there's no logarithm in it at all.
Mm-hmm.
And we will purposefully put a logarithm in.
Just to
be able to not have to work with something big and crazy and be able to break it down into a bunch of little pieces, all with simpler operations in them.
Yeah. Little bite-sized pieces. So would that be our answer? Is that the simplified? Yep. Okay. Wow. Feel so powerful. That makes so much more sense. Thank you for walking me through that.
Absolutely.
Sweet. I'm trying to think of, I wrote down stuff that I was struggling with. There's something else that is eating my brain up. Oh, I did have questions just like logistically. Mm-hmm. So because tomorrow's Veterans Day, are we not going to have class?
Oh, I guess we shouldn't, should we?
I'm cool if we do. I'm not against it, but I didn't know if you were planning on that or not.
Let me check the schools, whether the school has it listed as a formal. Because if it is a formal holiday, we really shouldn't,
Yeah.
For lots of reasons, but
for all the reasons, yeah.
If nothing else, just because, we celebrate veterans.
Right.
Yep, college is closed. for Veterans Day. So yes, we shouldn't and thus won't.
Okay.
Though, I don't know if you noticed, today's Tuesday. I
All day.
extended time on this stuff.
Yeah,
And
I
most
saw
people are
that.
done with most of that, but just in case people are still
Fancy
playing
pants.
with it, and moved even the test to on Monday.
Oh, you did?
Yeah.
Oh, cool. Yeah, for some
So-
reason it's still showing the test on tomorrow for me, but
Oh,
that makes me feel better
oh,
about
the
life.
date on that will probably still, actually that has our November 11th. So okay, yeah, it's still listed down here that way, but on the calendar it's not. But I can change that too. I have my own.
All the power. Sweet.
What's that, the 16th?
I think so. Yeah. 16th. What are you doing, math? Perfect. Well, yay, now I don't have to cram aggressively. Never goes well.
And this stuff, as I've said, and you're starting to see, none of these manipulations are difficult. They're just weird.
Yeah.
So they take
It
practice,
just feels
they
like a
take
foreign
exposure.
language. Yeah.
Yeah.
But definitely messing with it has helped a lot.
Cool.
I did have, I was having questions with 5.3 starting on question 16. My brain just decided to kaput on me. So.
Oh, that happens. 5. Let me just go to university. I can see exactly what it is. 5.3 question. Which one?
Starting on 16, I was having issues. I wasn't sure if there was like a formula or something I should be using.
Not really, not a specifically, but if we have, well, actually, let's do it that way. We're trying to make an, go ahead.
Sorry. Am I supposed to be using regression on my calculator for this?
No.
Okay.
You technically could, but no.
That's not the goal here.
Yeah. So if we've got y equals, let me see, which one do they want? Just to be careful here. Yeah. We're trying to make an exponential, so that should be y equals b to the x with maybe a compression factor there, right?
Right.
So we're trying to find that a and b. Just like when you're trying to find a line, right? You're trying to find that a and b, right? So we want to find that a and b. And what do we know? We know when x is equal to -3, y is equal to 1/2, right?
Right.
So this thing is equal to 1/2 when b is equal to -3. Fair?
Okay.
We also know that when x is 3, y is 32. So 32 is equal to a b to the 3rd.
Okay.
Right?
Yeah.
So we want to know what a and b are. And one of the ways to do that, one of the kind of nice ways to do that, is it would be nice if I could get rid of that a, right?
Right.
So I'm going to divide by something with that a in it. And specifically, I'm going to divide by ab to the -3.
Okay.
Because I know what ab to the -3 is equal to. What's ab to the -3 equal to?
It's equal to 1/2. Oh,
So
you're
that way,
really manipulating math, aren't you?
Well, what can we do in math? We can divide both sides by the same thing, right?
Yeah. All
Those are
right.
the same thing. We divided by it.
Like where your head's at.
So those a's went away, right?
Yeah.
And then 64 is then equal to b to the 6th.
All right. So now we just have to figure out the base. Or wait, we take the 6th root. of 64?
It's helpful to know that 64 is 2 to the 6th power.
I don't know anything.
Technically, there's a plus or minus there, but we know the
Yeah.
bases have to be positive, so we kind of
Okay.
ignore that. So then we
Look at
know
that.
what that base is, right? And then we also know that 32 is still equal to a times now 2 to the 3rd.
Right. So
Or you
32
could use
is
that one too. So 32, or you could have used this one as well.
mm-hmm.
So
Use whichever.
32 is a times 8. So what's a?
That's 4.
4.
A not very confident 4.
Not very confident 4, but a perfectly correct 4.
Sweet. Okay.
So that means our function is y equals 4 times 2 to the x.
Sweet. This isn't impossible. Imagine
Weird.
that.
It's just a lot of those. Wait a minute, am I allowed to do that?
Yeah, we're breaking all the rules this term. It's crazy to me.
Except
Okay.
we're not. It just feels like it.
We're breaking all the rules I made up in my head.
Fair, and that's actually a lot of what we are doing is breaking preconceived limitations.
Yeah. I don't know why I decided to set those up, but I sure did. Okay. Sweet. I feel like I am able to handle that.
Cool.
I don't know if I have any other pressing questions.
So if something comes up, let me know.
Yeah, for sure. I like that this ended up just being a tutoring session for me.
That's kind of nice. And I did record most of it so I can send it off to folks that might find it helpful too.
Yeah, I'd be very happy if I could look back at this.
Yeah.
That'll help a lot. Sweet. I think I'm good for now. I'm probably going to go mess with this and see if I confuse myself anymore.
Okay.
I'll send you a message on there if I do. But awesome. Thank you. I really, really appreciate it.
Oh, no problem. I'll talk to you later.
Yeah, have a great day. I hope everything goes well with your family.
Thank you.